Welcome everyone to the SHErobots first TU Delft SHErobots Cafe. I see that you all have your lunch and sandwiches, so thank you TU Delft Library. And my name is Vincent Salucci, and I want to welcome you to the TU Delft Library today. I'm very excited for this program and this particular event of the program. SHErobots is a program that is based around an exhibition of over 27 female researchers leading the way in robotics, and this traveled all the way from Australia to be put on for the TU Delft. And so I would like to recommend everyone, if you haven't had a chance to check out the exhibition, to please go there after the event. It's on the other side of the wall. And please check that out. And then what we really wanted to do is the SHErobots exhibition is also a platform, and so we wanted to connect it with the fantastic female researchers in robotics at the TU Delft. And we managed to do that for a series of cafes that highlights their research. So it is my privilege to present that to the TU Delft community and for those of us that join asynchronously online. So without much further ado, I will introduce the speakers and we can get going. We're going to talk about drones and touch today, so very exciting subjects. And we have demos related, so each of the two researchers will give a short presentation. We'll have a little bit of a dialogue. I'll moderate a little bit of a Q&A, and then we want to preserve a little bit of time to present the demos and to get you out of your chairs and to check out the fantastic robotics research that you can interact with a little bit. And we may even hover a drone, so we'll see how that goes. So just to formally introduce our speakers, in order of appearance, it's Yasemin Varder is an assistant professor in cognitive robotics department at the University of TU Delft, where she leads the haptic interface technology group. Her research focuses on leveraging our knowledge of the human sense of touch to create natural, compelling, and personalized haptic interactions in virtual environments, which can be utilized in communication, medicine, education, and human-robot interaction application. And Salua Hamaza is an assistant professor in aerial robotics and director of the Biomorphic Intelligence Lab at TU Delft, Netherlands. Her research focuses on the development of compliant aerial robots capable of interacting physically with objects and the environment. Her robotic solutions take inspiration from biological systems, leveraging compliance and hardware, software to advance versatility and autonomy in interacting drones. All right, Yasemin, would you please do the honors? I believe you're mic'd.
Thank you very much for Vincent, and the mic is working, so that's great. So good afternoon, everyone. First of all, thank you very much for organizing this beautiful event, Vincent, and thank you very much for joining us today. In this 15 minutes, I will talk about one of the most important and at the same time most neglected sense, which is our touch sense. But before I go into the details of touch, I want to first introduce myself. As Vincent said, I'm an assistant professor at the Cognitive Robotics Department of Faculty of Mechanical Engineering, and there I'm leading Haptic Interface Technology Group. So I joined in Delft in September 2020 as a tenure tracker. And as every tenure tracker, I was alone, sitting in my lab, alone, to think about what I'm going to do next. But over the next 3 years, I had the chance to work with wonderful people from different countries, different genders, and different levels. So everything I will talk about today is also thanks to them, because without my team, I would be just, again, alone and sitting in my lab. And also, I would like to thank our main funder, Dutch Research Council. Thanks to their money, we can do our wonderful research. Is it sound okay? I hear it a bit. Anyway. So as the name suggests, we work on haptics. Haptics means science of touch. And actually, our touch sense has two components. One of them is kinesthetic sense, which is sensing with our muscles or joints. And the other one is tactile sense, sensing by our skin. And our lab is mainly focusing on tactile sense. But why do we care? Why it is important? So if you think about all of your interactions in your daily life, think about since you wake up in the morning, since you come here, You touch hundreds of different objects and feel their physical properties, and also you manipulated them. And for those interactions, you mainly use your touch sense. Of course, we use our eyes and ears when we interact with different objects, but we mainly use our skin to feel them and also manipulate them. For example, if I didn't have my touch sense, I wouldn't be able to use this laser pointer, manipulate it, or feel its geometry. It was impossible. At the same time, we spend a substantial part of our lives in the virtual world, where we interact with our computers, smartphones, and tablets, or virtual reality glasses, or Apple Provisions, all these fancy things. So in those virtual environments, unfortunately, we mainly use our eyes and ears. Of course, we use a little bit of haptics, like for manipulating digital objects, but it's not for feeling their properties. Like when I touch an object in my smartphone screen, I mainly feel glass. And as a group, we think that this is ridiculous. Because if we spend that much time in the virtual world, and that world gives us a very unnatural interaction, we think that this shouldn't be in that way. So because of that, in our group, we would like to understand how human touch sense works, like what happens when we touch our physical environment, how we feel it, and how we can transfer this information in the virtual environment, like how we can digitize touch sense. And why this research is important? Of course, our main motivation is scientific curiosity. The main reason that we are doing this because we are a curious group. But of course, at the same time, the knowledge that we generate can be used for different applications. Everywhere that you use a smartphone or computer or any virtual, like any digital thing, you can embed touch sense. And we can think of like communication, healthcare, or art, all the different applications that we can use haptics. So I hope I convinced that this is an important field, so that I can say that by this motivation, we work in two different research areas, as I told you, like understanding human touch sense, and the other one is developing haptic technology. I say that they are two different areas, but actually they are not too different, because if you want to understand human touch sense, you need to develop technologies that can generate controllable stimuli. So for that, you need to develop haptic technologies. And at the same time, if you want to develop haptic technologies, you need to understand how human touch works, because otherwise it will be like a mechatronics lab. You have a bunch of devices, maybe they work, but if they don't give the correct stimuli, they are just useless. So you need to understand how human touch sense works. So for that part, for the understanding human touch, we look at our skin when we interact with the physical objects, and we look at what kind of mechanical deformations occur, how we can model this contact, and how these deformations translate to our perception. And for the technology development, we develop new haptic devices that we can interact in the digital world, and we develop new algorithms that we can digitize touch sense. So of course, I don't have time to talk about everything that we do in our group. I will mainly focus on one topic that encompasses both subjects, which is tactile texture digitization, and which is also something where my heart is. So I really want to understand how we can do that. So if we want to digitize tactile textures, first of all, we need to understand how people perceive textures. Like what happens when I touch this table, how I feel that table. So unlike the audio and visual sense, touch sense starts with a physical contact. So the process starts as soon as you touch an object. And then this contact creates a physical deformation on your skin, like a mechanical deformation or change in temperature, which can be sensed by our mechanoreceptors, which are our sensors under our skin. And these receptors can perceive different types of stimuli, like pressure, shear, vibration, or thermal stimuli. And then, when they receive this information, they can send through our neurons in terms of neural codes, so that it receives our central nervous system and makes us feel like, okay, I'm touching this table, and it feels in that way. Of course, in that process, we cannot say that it is completely irrelevant from our actions, because the way that I interact with this table, like if I am pressing on it, if I move my finger, all the physical deformations will be different. So we need to also think about that. Of course, I didn't add here, but our other senses, like our vision or auditory sense, also affect how we perceive tactile textures. So this is how, like a very, very summary way of how we perceive things in the physical world. But the aim is like how we can digitize it. So the idea is, this is something that I've been using since my PhD. So imagine that you are touching a real thing. In that sense, it's a penguin. So when you move your finger on the skin of a penguin, it creates certain physical deformations, right? What if we had a device that you can move your finger as you move on the penguin skin, and it creates the same physical deformations on your fingertip, so that it tricks your brain that you feel that like you are touching a penguin, but actually you are touching maybe a glass in that sense. How we can do it? I mean, it's a topic that I have been working for the last 10 years, so we still cannot generate the feeling of penguin skin, but we have something, you will feel it today. So the idea is, so unfortunately our field of haptics is not that developed, so we don't have protocols as in the other fields like in vision or auditory, but we can still look at them and learn how we can use those methodologies. For example, if you go to South Pole and see the penguins, you want to take a picture or video of them. So what do you do? So this is a kind of digitization of the visual part of the penguins. You take off your camera, you take a picture with it. That picture is saved as a file. It can be like a JPEG file, and then you need to have a device that you can render this image. That can be like your screen of your smartphone or a computer. So it has actually 3 stages if we make it in a very, very simple way, like recording, encoding, and rendering. So in our group, we are working in all these 3 processes and also the perception part. And I will talk about 2 projects that we are working on right now. So one way to do that, one way to digitize tactile textures, in the virtual environments, is recording the tactile data as the way that we do for images. So with Jagan in this project, we call it FieldSurf. Jagan is a PhD student in my group. So we recorded data when people are interacting with real textures, and we recorded interaction forces, and then we fit those forces in the texture models. You can think like a JPEG file, but it is more like how we can model these interactions. And then we render them through an electro-vibration display. These devices can generate, it's a capacitive touch screen, but instead of sensing your fingertip, we can actuate it. How we do it? We send a voltage signal to the conductive part of the capacitive screen, and when you move your fingertip, it can generate controllable friction and roughness on a flat touch screen using electrostatic forces. What we do for different textures, we record the data, we make a model, and then we render on this display. So we call this device as a FieldSurf, and with this device, we can only render friction and roughness fields of surfaces. Right now, we are working on how we can optimize this modeling process, because there are different ways of it, how we can perfect it. Hopefully, by the end of Jagan's PhD, we can make a perfect model that we can render all different textures. But I should say that even though we made the best model, with this process, with this rendering device, we can only create certain realism, because these devices can only generate vibration and shear. And when we interact with real objects, we also perceive other properties, right? Like their thermal properties or their softness. And with this flat touch screen, we cannot render those things. Right now, when you feel the textures that when you feel his demo, you will see that, okay, we can generate some sort of realism, but they are not exactly matching. So because of that, we are also working that how we can encode multi-sensory information and how we can render it in the digital environment. So the first thing that you need to do for that to get data, and this is how we started. So we created a multi-sensor database of finger surface interactions that we collected data from 50 different textures, and we collected both visual, auditory, and also haptic data. And while people are interacting differently for different surfaces, like not only sliding, but like pressing, tapping, or contacting statically, and we collected different informations that can span all sorts of haptic information. But of course, when you have the data, then the next thing is you need a device to render it, right? With Bense, who was a master's student in my group, and he worked as a research engineer, for that we built a pan that we call field pan that can render it all. So the working mechanism of the pan is similar to how we generate textures on this field surf, like electrovibration displays. This time, you interact with a capacitive touch screen with the pan. You send the voltage signal again to the capacitive touch screen, but it has a conductive tip. So when you move it, you can generate friction and roughness fields, again on this flat touch screen. But we also put a voice code actuator in the vertical direction that you can also generate compliance information of the objects. And then we have a Peltier cell here that can also render temperature. So with that, we can say that we can render all the important information with the pan, but of course, this is not how we interact with real objects. We interact with our hands and skin, right? So the next step is with Heaven and Koa to make a multi-sensor device that we can interact with our bare fingers. But for that, we need to do another presentation in 2 or 3 years, maybe. So that was all. Thank you very much. So I talked a lot. So I think talking only can do a bit thing for the haptics. So after Salua's talk, after our dialogue, you should come and feel our devices, and then you will understand better, I think, what I am talking about. Thank you.
So, good afternoon, everyone. Can you hear me well? Nice to see you all here. I see several familiar faces, and it's really nice because some of you are part of my journey here at the TU Delft. You may ask yourselves, what do drones have to do with touch in the first place? So, well, hopefully by the end of my presentation, I will enlighten you. Oops. I will enlighten you on this. It was very nice to see, like, Yasemin's insights on haptics. And essentially, in robotics, a large part of the scientific community is looking at this robotic touch or manipulation. The drone community in the robotics community looks at drones and mostly research is on motion planning and vision-based navigation. This means that the majority of the people in my community look at the sense of vision to do things with drones and make them fly around, avoiding obstacles and so on. However, a very, very few people look like how we can give drones a sense of touch, meaning then how can we make them do things and interact with the environment and objects. So it's a very, very niche research areas, and it's also very hard to research on. So in my lab, we look at physical interaction with drones. So drones that can actually manipulate objects in the environment, or they can manipulate the environment itself. And why is this useful to begin with? Well, because in this way, we not only use drones as flying cameras for us that take cool videos for us, but we can also use them to access places, environments, or objects that are very hard for us to reach, and maybe there they can do something with those objects. So my group in my lab looks at different things. So we mainly focus on designing these drones, designing their bodies, but also like controlling their behavior. Today, I only have time to cover a couple of projects, but I'll give you a glimpse of what the others do as well. So the application I will start with is environmental monitoring. So this is something I've been doing for a few years now. So trying to convey these applications of drones in environmental monitoring. No? Not working? So maybe I need to... Maybe try to unplug the... technology. Maybe we need to unplug this.
Yep.
Yeah, okay, now it works. So, this is a very nice video that me and my team captured a few months ago. So we went to Singapore, outside the metropolitan area of Singapore. There is a very extended rainforest. I was there with my team of students, and we were there because we wanted to show that drone technologies can help with environmental monitoring. And specifically, as you can see, these kind of environments are very widespread. They're also very inaccessible, like for humans, but they're also very intricate. Why do we bother to look at them in the first place? Well, forests are very important for the survival of our species, and not only us, of course. They host millions and millions of species of biodiversity on our planet, yet they cover a very small percentage of land. They're not only essential for us, but of course they're also essential for local communities and indigenous people that live in these ecosystems, and they live in perfect harmony with them, getting food, shelter, or even medicine from these ecosystems. So it's one of my priorities as well to show how robotics can help with these kind of applications and show the potential of drones within this. So in my career, I've been looking at using drones to basically place sensors around in the environment. So you can imagine a drone which flies for very little, unfortunately, maybe 15 minutes. So it cannot do much, but maybe you can go to a certain area and place a sensor. Yeah, place a sensor that monitors something. How are these things done right now? So we have mostly forest towers, which look like this. And we also have, of course, manually deployed sensors in the environment from ecologists. So neither of them is really scalable, right? Because or cost-effective, because, for example, for the ecologists climbing trees, I speak with a lot of biologists in the field, and really spend weeks on end in the forest to try to study these ecosystems. So it would be really immense help for them to have these operations a little bit more automated with the help of drones. So as I said, the field of drones is really, really advanced in computer vision. So it's really closely tied together. So drones now are at a certain point where they can autonomously navigate in the environment, and they can cover very wide areas. So they do this very nicely. However, the problem with drones is that they have a very short battery life, as I said. So if we were to monitor these kind of large environments, we will need multiple missions to send the drones and collect some data, and then again and again. Hi.
Swap you out. Just, you can just put it down, I think.
Right, okay. So as I said, so we can have these drones going with multiple missions to these environments, and they collect some data all the time. So this data may be very good, may have very good spatial resolutions because the drones can fly very far away, but they have very low temporal resolution, right? So they don't really help much the ecologists in learning about long-term changes in the environment, maybe caused by human activities and so on. So there must be a way in which we can use drones to help with this part as well, so to kind of like overcome the problem of endurance, mainly. Another aspect is also the noise. So oftentimes these drones are very noisy, so when we deploy them in these environments, they actually disturb the biodiversity. So one of my PhDs is looking into this. So how can we give drones longer endurance, but also tackling the noise problem? And we look at how birds do things. So of course, birds perch on tree branches, and they do so to recover their energy. And of course, as they lay idle on tree branches, they don't spend any energy. And we could replicate this behavior on drones. So in this way, we can, for example, we can increase the endurance because a drone can land on a branch and sit on the branch for as long as it needs with the motors shut down. And it can become quiet as it sits on the branch. So what would it do on sitting on the branch? Well, the idea is that in itself, we can equip the drone with a lot of sensors, and having the drone has a mobile sensing device. So in this case, for example, we can have acoustic sensors or humidity sensors or other type of sensors that monitor the environment for us. Now, the challenge on the scientific part is that, okay, so these branches are often inclined. They're really hard. It's really hard to really land a drone on these kind of surfaces. And actually, with quadrotors specifically, which are the commonly seen around type of drones, these operations become even harder because a quadrotor cannot, hold a position that is inclined for a long time. Actually, only a few milliseconds. So to overcome this, we looked at design first. So we designed some sort of, we can call it like mechanical claw, inspired to birds, that would grasp ultra-fast the objects in the environment. And the ultra-fast part of it is very important because, as I said, we can only cover, with control theory, we can only cover a certain point, but then still we need to do the operation in a very agile way. So we need to have a gripper that is compliant because, of course, we land on soft branches, so we don't want to damage things. But at the same time, it needs to be ultra fast. So we did this using mechanical compliance, as I do with all my projects. And with this, we kind of deal with the uncertainty of the objects we land on. And you can see a mini version of it here, and later you will also see it activated. Then the second component of this project was also like, okay, how do we land the drone on the branch? So there is also a control part in it. So planning the motion such that the drone can land on the branch. This is also not straightforward, but based on the state of the art already, there is a lot of research into this. So we only needed to add the component of the branch. So we want the drone to perform the motion such that it arrives with a zero velocity on the branch, And so we were kind of like the first, let's say, result in the community to show this dynamic landing on these inclined branches. Now, with this, you get an idea. So we also have other type of drones with different designs. And the idea is that with these kind of designs of claws or arms or limbs, we can give drones more versatility because they can actually do things in flight. Another part of my interest in this research is also looking at navigation. So in this case, as we will see in a moment, we use the sense of touch for many things, as Yasemin said. And one of the things is actually for navigations, especially for animals. So in these kind of environments where we really cannot use any vision, for example, I'm talking about dark caves or, in general, environments with low ambient light, or, for example, in smoky areas or dusty areas, the sense of vision is impaired, essentially. So we cannot really count of all the amazing results done in the drones community. So how can we deal with this? Well, so far in these kind of environments, people start to pack a lot of heavy sensors on drones that can deal with this lack of light. Problem is that as soon as you do that, the flight time drops even more. So instead of having a 15 minutes flying drone, you have it for like 5 minutes or so. And it's also very computationally heavy to do all the behavioral or this kind of like think of the actions that the drone needs to do. So in my case, I tried to look at nature for this kind of inspiration for this approach in navigation. And this is very nice because this is a video from maybe university in the US. But basically, they showed here that rats use whiskers, for example, for navigation. So much more than that, actually, the rats move the whiskers around, and with these whiskers, they can sense objects, they can sense the shape of objects, and then they can also make decisions on navigation, how to go around these objects. And they find a way out of mazes in this way. And they do this in complete darkness, and only using the whiskers. So this is like pretty amazing, and it's a completely different way of seeing things or not seeing things. And rats are not the only ones doing this. So of course, rats, as I said, they do this for exploration, but cats also do this a lot, especially with the manipulation of objects. So with whiskers, they can localize where the object is in front of them, and then they also can do they complement it with the manipulation. And also, seals, you do that a lot. So whiskers are also used in underwater to understand the flow around them, but also to understand texture. This is pretty amazing. So maybe one day we'll get through all of these things, but I wanted to start with navigation first. So the main idea for this project was to, well, first of all, let's build a whisker, a whisker sensor, which is like this bio-inspired sensor. We had a look at like the state of the art, like, okay, so when you design whiskers, you want to have them very lightweight, and which kind of information do we need out of the whisker? So we spent a little bit of time on this, and essentially we went with something that can tell us the direction of the force of the deformation. So we have this whisker, and we move the whisker around, and we want to understand where the force is coming from. This is very important and actually very much neglected in the community. So second part is that we process this information in some way, and with whiskers it's not super straightforward because we have, let's say, multiple outputs. So if you can understand this figure, is basically telling us if we want to understand where the whisker is being touched, at which distance, we see that touching the whisker at different points around the length will cause the same deformation and the same amount of force. So how can we decouple the two informations? Well, we solved that with machine learning. And so now the next step would be to look into navigation. So at first, because we rely on touch, we want to look for touch. So meaning that we don't want to avoid obstacle, but we want to embrace the obstacles around us. We want to make contact with the obstacles, and we want to be able to safely navigate around these obstacles. So the first part is to obviously look for contact. Then once we are in contact, we have some form of deformation. We have a whisker drone, so a drone with many whiskers around. And so we can do contour following. So imagine like you are, I don't know, in your home, and you don't have any light in the house, but you're still able to navigate your way out of the, I don't know, the bedroom, right? So you have no light, and just using your hands, you would touch around in the environment and then kind of like follow the wall until you're out of your room. We want to replicate this with the drones with whiskers. And so the main application for this is really to show that these drones can fly in complete blindness. For example, in caves or in GPS-denied environments. Or for example, with some of the latest space exploration missions where they show that we have drones also in lava tubes and caves, and we want to make their navigation as lightweight as possible. So that was it. So I also want to acknowledge my team because, yeah, of course, we wouldn't be able to do such interesting and curious research without them. So all of them pretty much work on the kind of drones design and make them more compliant to make them more versatile. And the idea is that we want to boost autonomy and also their capabilities. So we want to create drones that are not only able to fly around, but they can maybe locomote on the ground, they can manipulate objects, they can perch, they can hang on structures, and so on. So if you want to know more, just like scan the link, you will look at the Biomorphic Intelligence Lab. So yeah, I also welcome you for a demo. Like we have the mini whiskered drone demo. And we also have the bigger one, the bigger version, where we have whiskers all around the drone. And then this one cannot fly in the library, but at least I can explain you how it works. Okay, so yeah, that's all.
I think we'll share this mic and invite Yasemin up again. Maybe I have a few questions for you, and then hopefully we can open it up to the audience to have a few questions. Thank you both for your marvelous presentations, and really look forward to the demos here shortly. But one of the subtitle for the exhibition and the program is Ecologies of Care. So I was curious how you see your research as an act of care.
Yeah, thank you for the question. So I think specifically one of the themes of the Ecologies for Care is really centered around how, for example, women bring a different kind of intuition or creativity to research. I think creativity is really a strong point, at least it was a strong point for my group, in the sense that thanks to the creativity of the designs or the ideas, we were able to stand out. It's really hard to, stand out in a community where people, for example, in my community specifically, many people work on control theory, so it's really hard to stand out unless you have a very creative idea. In another way, I would say, well, besides the inclusivity of the group or the diversity of the group, I would say also inclusivity in technology. So what is the purpose behind the work we do? And who is it useful for? So this is something that, for example, in my case, I try to look at like inclusivity towards the environment and try to make these kind of technologies less intrusive, less rigid, and less, let's say, dangerous in this way. So this is kind of my take on the Ecologies for Care.
On my side, I can say that we are adding another modality. So most of the things most of the devices that we have around, they design for vision and auditory fields, right? We are adding touch sense, and when you add another modality, you are increasing the diversity in any case. So imagine that for the devices that we build, people who cannot see, they can also feel the textures that we can render, for example. Or I cannot say that we have direct applications that we work in our group that these are the examples of the things that we do in the ecologies of care branch, but I can say that all the things that we do, both Salua and I and our teams, can be used to increase diversity in terms of research, if I understand the question correctly.
You do. I was also curious, I mean, your colleagues at the TU Delft, but one of the, I think the powerful positions of the library is to try to bring people together from different faculties and have conversations. And I'm actually curious if you could just take a moment to respond to each other's research just with insiders, expert knowledge. Is there anything you would like to, just comment upon or point out or anything like this?
Yeah, I mean, I would love to see at some point like my drones discriminating textures. So I wonder like if at some point we could do that, would be very nice. I mean, for me, maybe the question would be like on the kind of challenges, because for texture discrimination, for example, I wonder like, how do you even go about choosing or understanding? Like there is so much more outside robotics or signal processing that you also need to know. So how do you get that exposure to the kind of knowledge? Like how do you even go about with these like multidisciplinary projects?
By just talking people, I guess, thanks to these kind of events that we can talk about research, listen to other people's research, going to other conferences. But sometimes it's also hard because when people talk with different languages, like not literally languages, but in terms of research language, sometimes you feel lost. But by just talking, and most of the research that we build, they came out in coffee corners. Like we were just drinking coffee. Oh, okay, this is what I do. What do you think? Like I think just interacting with people, talking with them, discussing them, and joining this kind of event. So you did a great job. So you made a first step, I think. So this is one way to do that. And I'm really hoping that maybe we can work together, that make your drones feel textures. That will be amazing.
I have a question about the other possibilities regarding in this. I'm in aerospace faculty, so I was wondering about other possibilities on drone vision possibilities. For example, using the BAT's ultrasonic sensing capacity. Have you ever thought about that other possibilities for sensing without vision?
Yeah, thanks for the question. Well, I must say yes and no. So in one way, I know that obviously other sensing modalities are there. For me, I do it a little bit selfishly, that I want to really develop the sense of touch that right now it's completely non-existent. And I want to show how it's very useful for interaction, of course. So on my side of things, like, we do many daily tasks without even looking. So for example, every morning I kind of like tie my necklace in the back of my neck, and I don't see what's behind, but I'm able to do it. And it's a very precise and accurate motion or a task that I'm doing without any vision. So we kind of relying on amazing tactile feedback in our body, in our hands. And in the community of drones interacting with the environment, this is extremely rudimentary. There is no tactile sensing whatsoever. And the operations are done kind of blindly, like the drone doesn't know what's happening, it doesn't know what's holding, if it's not holding something. So for me, primarily, I want to focus on the sense of touch.
I do know that, to go out in the real world at some point, we need to compensate or we need to complement with vision, because of course, to see an object, you need to see the object in the first place that you want to interact with, and then get there. Then once you are close to that, you can touch it. But for now, okay, so this is also not my outside of my scope, but I hope to collaborate with people that already work on vision, and there is plenty out there, so yeah. And also maybe incorporate other sensing modalities for sure. Actually, on this, one of my students, Sunyi, who is here, we are looking also at airflow sensing. So even just looking at how we can feel on a drone, the airflow around it and take smart decisions just feeling the air moving around us. That does include the sense of touch. But in a way, this is also what kind of underwater, what animals underwater do. So yeah, I look at those kind of things. I would love to one day incorporate more modalities for sure. Yeah.
Any other questions?
Yes, this is a question for you, Yasemin. I'm really interested in sort of measuring surfaces, and you talked about trying to display these surfaces more. My question is, which lessons do you think you could apply from visualizing or replaying this tactile information to also sensing tactile information? It's sort of the inverse problem. And sort of as a follow-up, how do you think we could get this information into sort of a lower dimensional space? Because usually you display it sort of as a image, which is very high dimensional. And how can we extract these features to try to display it in a lower dimension?
You ask a very hard question that we ask ourselves every day, but I can try to give some of the lessons that we learned. The first lesson I think we learned, not to think of surfaces as images. So because when you just look at the images, we have lots of image processing algorithms, right? We can extract features and everything. But tactile textures are different. It's not only when I first started working on this topic, I was thinking, okay, so imagine that you have a grayscale image, and depending on the gray level, we can display amplitude. So that's how I started. And it doesn't feel realistic at all. Of course, you can feel some sort of a geometry or a shape. We can display that information. But if you want to really display realistic surface, like of my jacket, you should stop thinking it as an image. You need to think about what is the information that my sensors will get. And then we come to the point that, okay, what do we sense? Like when we move, when we press on it, you perceive pressure, right? But when you move it, you perceive also shear, vibration, and thermal information of the textures. So if you can render those things, if you have a device that you can render all those things, you need to measure those things in a way that you can render them. So it's like a bilateral problem. Yeah. Right now, we don't have devices that we can do it all. So that's why in the beginning, we were not measuring everything perfectly. So you will also see that by just measuring forces, when you move your fingertip, it can only give some sort of information, but not everything, right? So I don't know if I'm explaining your question perfectly, but it depends on the aim. If your aim is just displaying something, yeah, you can look at them as an image, and then you can render the amplitude based on the grayscale of the image. But that can only give you some certain information. If you enlarge your space, like the dimensionality of the things that you can measure, that you can render with the device as well, that can be the best of the world. But we are still working on it.
Thank you.
You're welcome.
One more question?
Thank you. My question is, again, it's about, because I don't know how you guys do these things, but is it really, really hard to make, for example, a screen change its temperature when you move your finger around it? What do you need to develop this kind of technology?
So giving a temperature feedback is not hard. The problem is to make a display that can change the temperature so how can I say, like, our thermal sense is not perfect, right? It doesn't change very quickly, but at the same time, our thermal actuators cannot change very quickly. So imagine that, you will also play with the pen, hopefully. You will see that we can change the temperature. We can even give a certain curve that we can change this information, but it is not that fast. So imagine that you have a screen. You want to, for example, perceive the forest that Salua showed. In some part of this forest is a cold part, and the other part of the screen there is a bird, for example. It is very hard to make a screen that can display these two information that fast when you touch different parts of the surface. Because we don't have pixelized thermal devices, which can also show visual feedback at the same time. So that is the challenges for the thermal part, and I can talk until morning the challenges about the other parts of the thing, but I'm very hopeful. Because technology is changing, and there are lots of developments in the material field that we rely on. So I'm not a material scientist. I work with material scientists so that they can make devices that can change their temperature or textures using smart materials, for example. I think it won't be too late that we can have that devices soon, but not now.
Hello. I think that concludes the speaking portion of the event. So can we thank again our two researchers, speakers, SHErobots. And we're going to fire up the demos and see what kind of trouble we can get into. And I just want to point out also that I want to thank you for joining us again. And just to wrap up this speaking session, we have the next SHErobots Cafe will be on March 8th. Instead of a lunch event, it will be an afternoon one, so it will begin at 1600. And I just want to point out that's also International Women's Day, and so there will be a large program in the aula that D&I and DUIS are putting on, and they've both been collaborators in this program, so we certainly want to support them. And then you can end your day in the library with talks by Professor Henrietta Beer and Professor Mariana Popescu from BK and CEG respectively, and we'll have a robot in here doing a planting demo, as well as looking at some textile robotic building techniques. So it should be pretty exciting. But let's get more into some haptics and drones. So thank you.